Alrighty, hi guys. This is the second topic of the semester, second lesson video for the second topic. This topic, 1.2, is called Economics as a Science. It is also kind of covered in chapters 1 and 2 of your textbook, but this and the previous topic are kind of just more concepts that I kind of created on my own that I think do a good job introducing you to economics. So as a reminder from topic 1.1, we talked about the social side of economics as a social science. We talked about the word scarcity, the idea that our wants and needs as human beings is unlimited, but our resources are not, so we have to make choices. And so economics is looking at how we make those choices, how we make better choices, how we deal with scarcity better. We talked about how most modern economies are mixed economies, which means they have a mix of a market economy and a command or planned economy, those regulations about how we deal with scarcity. And we talked about making choices at the margin, as well as several other economic foundations, and how we always weigh benefits versus costs. So typically at the beginning of each topic, I will talk about stuff that we've discussed in the past that's going to be relevant moving forward. So these 3 bullet points are going to tie into this next topic. So the key questions are: how do economists study the economy? How do resources flow through an economy? And how do economists use data and graphs? So the last topic talked about the social side of things. This is talking about the actual science part of things, the process that economists go through. And it's a little bit more technical. So one thing that economists use is something called the scientific method. So this is a breakdown of the scientific method that you should see in most of your science classes, from chemistry to biology to physics. And economists use a very similar process when studying the world around us and studying human behavior. Now, we do tweak this process a little bit. We are not a traditional science the same way the physicists, biologists, and chemists are, but we use a similar process to solve problems. So the first step in most scientific method is to observe a phenomena, which is just something cool in the world that you'd like to help explain. So an example of this relevant to economics might be the recession that we're going into related to the coronavirus pandemic. So I have this crazy thing happening in my economy. I want to explain it. So step 2 is to develop a hypothesis, which is a proposed explanation. So maybe my hypothesis is that if there is a global pandemic like coronavirus, it'll cause most economies in the world to go into a recession. So there's my theory. Then I'd come up with a model to test the theory. So this is kind of like the method you would use in your science classes, like the steps in your experiment. But in economics, it's going to be a little bit trickier. It's kind of like a theory or a proposed explanation. So to test my hypothesis of whether a global pandemic would cause a recession, I might use a model that we learn in macroeconomics called the aggregate demand, aggregate supply model that predicts recessions and expansions in the economy, something called a business cycle. That would be our model. And then step 4 is to actually do your experiment. In economics, we would collect a bunch of data to run our experiment. So I would look at all kinds of economic variables that determine whether or not we're in a recession. We might look at the production in the economy, which we call GDP, gross domestic product. We might look at the unemployment rate in the economy. We might look at the inflation rate or the level of prices across the economy, all kinds of variables that we could use to predict those sort of variables. And we'd also look at what could cause them to fluctuate. So maybe I'd look at, infection rates for the coronavirus. I would look at the spread of it and the severity of the symptoms and all that stuff, and try to relate it to those economic variables we were discussing. And then step 5 is to run my experiment, look at the results, and then I will revise or refute that hypothesis, whether or not the coronavirus caused a recession, or tweak it a little bit, and maybe certain responses to coronavirus caused recessions. And then you repeat the process over and over again. So hopefully, roughly, this looks like the scientific method that you learned in your traditional science classes. The steps might be broken down a little bit differently, a little more detailed in, say, a biology class, but the process is very similar with economists as other scientists. All right, so economists differ from traditional scientists in one really key way, which is that we don't have a laboratory. So in your science classes, typically before you can do your lab, you have to go through all these extensive trainings, partially to help you with your safety, but also to keep your lab environment pristine and controlled. Part of doing good science is making sure the environment does not affect the outcome of your experiments. But in economics, the world is our laboratory, and the world is a complicated place, and we don't have this nice, clean laboratory where we can control all the conditions to run our experiments. So we have to make some adjustments based on that. One way that economists adjust for the fact that they don't have a laboratory is how we phrase our conclusions, our theories, and our hypotheses. We try to stick with something called a positive statement when we're developing these, which just means we are looking to prove or disprove some sort of fact. So a positive statement can be tested and validated. And we want to stay away from something called normative statements, which are opinions, and because they're opinions, I can't test them and prove them right or wrong. So economists, we try to stick with positive analysis, which means we make positive statements to test and make conclusions about the economy. So positive statements, not the same thing as a positive incentive like we discussed in previous topics in 1.1. A positive statement means I can test it, I can validate it, I can prove it right or wrong. So an example would be of a positive statement would be the sky is blue, right? I can test that, prove it right, prove it wrong. A normative statement would be something like the sky should be blue or the sky should be green, right? I can't really test or prove that and collect data to back it up. So we want to stick with those positive statements. So here's some examples, just so you get a feel of what's positive versus what's normative. The first one, rich people should be taxed more. So an important word in there is the word should. That kind of is a giveaway that this is a normative statement because you can't really prove or test should, right? By what criteria does should prove to be true? Now, on the other hand, number 2 says more taxes on the rich will increase tax revenues. So tax revenues, that's the amount of money in total that the government can collect from a tax. So this one I could actually test, right? I could look at different tax rates on rich people, look at the different corresponding tax revenues and say 2 is correct or 2 is incorrect. I can test it, I can validate it, I can prove it right or wrong. Now, if 2 turns out to be true, it does not necessarily mean that 1 now is a good statement, right? We still don't want to make these judgment calls in economics. We want to leave that up to the political scientists. That's more their field of expertise. We just want to stick with the science of it. So an economist might make a statement like number 2 and would probably try to stay away from something like number 1. All right, third, everyone should donate to charity. Hopefully you can see that that's more of an opinion. If you see that word should in there, that's almost a dead giveaway that it's going to be a normative statement. 4, government intervention in markets is bad. This is going to be normative as well. This one's tricky because the word should isn't in there, but there is this really subjective word bad. So it's really hard to prove or test bad. So that's going to make that normative. 5, economics majors earn more on average than sociology majors do. That is going to be a positive statement because I can test that, right? I can collect information on salaries of economics majors and sociology majors and compare the averages. For the record, number 5 turns out to be true if you're interested. Economics is a fairly high-paying social sciences field. All right, so another way that we adjust our experiments is we use something called a model, an economic model. So like I said, the world is our laboratory. The world is a complex place. So economists create simplified versions of reality to help us understand that complex world, take out some of the complexities. So a model, this definition in bold, is a simplified representation of some sector of the economy that includes enough key features to help us understand it. So the best example I can give you of a model is like a map. So if you were trying to get from point A to point B and you were to open your favorite Maps app on the phone, it would give you basically a route, right? It might tell you the names of the streets and where to turn. If you have one of those fancy apps like Waze, it might tell you if there's a cop along the way. But your map isn't going to include every single detail along the way, right? It's not going to tell you the number of trees you pass. It might not even tell you every stoplight or stop sign that's at an intersection. It's not going to tell you necessarily any potholes all along the way, though some of those apps do have those details. And the reason, though, that some of those details have been taken out of the map, it's not a perfect representation of what you're going to encounter along the way, is if we don't take out that unimportant stuff, it would be really hard to read your map, right? It would be really hard to follow Google Maps or Apple Maps if every tree, if every car on the road, if every obstacle you could possibly encounter along the way was on there. So that's the same way economic models work, is we want to keep enough of the important stuff like the street names and when to turn where, but take out some of the details that make our real world difficult to understand. So they're also sometimes called theories, and this next bullet point, models use assumptions. So assumptions help us simplify those models. So when you're building the model, like you're creating a map, you make assumptions about what the important stuff to leave in there, in the map is, and what stuff we can afford to take out, right? Just like the trees probably aren't going to bother that many people. And so those assumptions are really important to help make our models useful, but they can also be dangerous because if we make the wrong assumptions and we take out details that are actually important to people, then maybe you can't get from point A to point B. So we evaluate our models in economics by going back through and repeating that scientific process. We decide a model is a good model if it predicts accurately. So I also have this little picture of a paper airplane on here. Paper airplanes, that's another simplified version of reality compared to a real airplane. Definitely simplified, but can help you learn something about aerodynamics. All right. In models, economists distinguish between endogenous and exogenous factors, or endogenous and exogenous variables. They're just all the things that can complicate your model. So if a variable or a factor is endogenous, that means it's controlled within the model. So suppose you were building a paper airplane. Certain variables like the type of paper you used, the length of the wings, the length of the plane, all of that stuff, those are examples of endogenous factors. You control them as the creator of the model. Now, an exogenous factor would be if you went to fly a paper airplane outside and you were comparing different designs of your paper airplanes, you've got different endogenous variables that you've made. If you were to fly multiple planes, things like the wind or the rain or the humidity or bugs flying by, those are going to affect your model's accuracy, but they're outside of the model. You can't necessarily account for them because they're exogenous, they're external to your model. So as economists, we got to be careful, think about both endogenous and exogenous changes that can affect the model's accuracy and make our results, make our predictions a little fuzzy. All right. So we talked about assumptions used in economics. One really important assumption that we'll use in this class is something called ceteris paribus. It sounds really fancy, sounds really complex, but it's just a Latin phrase that's a fancy way of saying all else equal. So we use it to build economic models because it helps us keep everything constant and just change one thing at a time. So for example, if suppose you were getting sick regularly, your doctor might recommend that you start taking certain things out of your diet. Maybe they say if you cut gluten or dairy or animal products, something like that, to try and resolve any health issues you're having. What you would want to do is you would want to change one thing at a time. If all of a sudden you cut gluten and dairy and meat and all kinds of things from your diet and suddenly maybe your health issues resolve yourselves, you change too much at once. It's hard for you to figure out, was it the gluten or was it the dairy or was it the meat that was making me sick? What your doctor is probably going to recommend you do instead is just change one thing and keep all else equal, ceteris paribus, and see if that makes a change. So if you're having some stomach issues or health issues and then you cut dairy and it doesn't make a difference, now I've learned that dairy is not the issue. So I can incorporate dairy back into my diet and then try cutting gluten. And then it turns out my health issues go away when I stop eating gluten for a couple months. Now I know, because I kept all else equal, that gluten was the problem, and then I can learn something about it. So we do the same thing in the economy, is if we want to see how a certain sector of the economy works, let's keep everything constant that we can, just change one thing and see if we can find the result on that sector of the economy. All right, so here's an economic question. Who gets paid more? And we're going to try to look at these variables ceteris paribus. It might seem easy enough, but it's really easy to think about all of the combined variables when I ask you about it. But I just want you to focus on this specific one variable. So everything is the same between two workers, and the only thing we're changing is everything that's kind of in these indented bullet points one at a time. So two workers who are exactly the same in every single way. The only difference is this one variable, educated versus uneducated. Hopefully, educated individuals will be paid more because education is going to amount to a higher skill level, right? That's the dream. That's why you're here taking this class, watching this video. Skilled versus unskilled labor. Skilled labor is probably going to be paid more. A worker right out of college or an older worker. Now this one can get a little bit trickier. So sometimes older workers might be seen as more experienced, so maybe the older workers paid more. However, past a certain point, maybe being older isn't to your advantage in a hiring scheme. Remember, we're talking about these variables ceteris paribus, so same workers with the same skill level, same education level, same everything, just one right out of college versus one who's older. It's harder to see if age is really the only variable we're weighing here. Maybe earlier in life, being older is going to be more to your advantage, and then later in life, there's sometimes cases of ageism in the workplace where actually being younger might be to your advantage. New employees versus veteran employees. Probably veteran employees are going to be paid more just because you've had more time to work at a company. And then this last one always throws people off. A safe job versus a dangerous job. Believe it or not, ceteris paribus, all else equal, dangerous jobs actually make more money than people who work safe jobs. Now you might be thinking to yourself, hold on, I can think of a lot of safe jobs and a lot of dangerous jobs, and all the folks working the safer jobs tend to be making more money. And while that might be true, it's not necessarily true ceteris paribus. So if I keep all else equal and we just manipulate the safety variable, people are going to have to be compensated for the fact that their job is dangerous. So if you're thinking of dangerous jobs versus safe jobs, think if those safe jobs that are making more money also require more education or more higher skills or more experience. The answer is probably yes. But if we just look at the variable ceteris paribus, maybe two workers with the same education, same experience, same skill level, maybe low-skilled jobs just for the sake of it, maybe like a waitress versus someone who works on that show Deadliest Catch. The Deadliest Catch guy is going to make more money. They're both fairly low-skilled, low-education jobs, but because the Deadliest Catch guy is working a very dangerous job, he's compensated more handsomely than someone working in the service industry. So the more dangerous jobs make more money. All right, so in economics, we also have this assumption called the rational behavior assumption, which means kind of what we talked about back in the first topic, the idea of marginal analysis, that we should always do an action when the marginal benefit outweighs the marginal cost. That is what rational behavior means. We assume all humans act rationally. We only do an action when the benefit outweighs the cost at the margin. And irrational behavior would be knowingly making a choice where you know the marginal cost outweighs the marginal benefit. Now, there are exceptions to this rule. There's a whole branch of economics called behavioral economics, where people look at when people make bad choices. They make choices either knowing the costs outweigh the benefit, or they don't have enough information to weigh the cost versus the benefit. But because this is an introductory economics class, we are going to stick with the rational behavior assumption that most people will make a decision to purchase something, to invest in something, to go to college, to take a job, all kinds of economic choices when the benefit outweighs the costs. All right, so some objections to what I talked about so far. So these are kind of some common criticisms that economists get about our models and about our process and about our assumptions. So I kind of want to address them right off the bat, hopefully dismiss them, so we can kind of move forward with what I just discussed. So there's two primary objections here. First, that people, firms, and society don't act like this, meaning they don't act rationally, like I was talking about on this first slide. And they say people don't act rationally, either one, because they don't have enough information, or two, they simply aren't careful enough. So this might be logical to you. You might hear the word, oh, economists assume everybody acts rationally, and you can think of some examples of you or your friends doing some pretty silly stuff or making some pretty dumb choices. And that's true. Maybe when you go to the grocery store, you don't precisely read every single price tag and decide whether that loaf of bread is really worth $4.99 or whatever it is. You just kind of haphazardly throw things into your grocery basket that you need. However, even if you aren't that careful or don't always have the right information, we still assume that people generally, in the long run, do act this way. They do kind of make this choice, even if people aren't this careful, even if they don't have the right information. So the best analogy I have for you is to think about shooting a basketball. Think about economic behavior and rational behavior, like accurately shooting a basketball, making it into the hoop. And so I have two people standing next to each other at the three-point line, ready to shoot this basketball. One of them is a physicist, and the physicist has all the information, right? The physicist can figure out the perfect trajectory and angle and velocity at which he's got to shoot that basketball to make it into the hoop. And the guy standing next to him is Steph Curry, right? So a professional basketball player who probably does not know the exact angle, could not tell me what angle he shoots a basketball, or the velocity, or the trajectory that he's going to use to make it in the hoop. And he's not that careful. He's not thinking that deeply about it. But if I asked you to place your bets on which one of them is going to land that basketball in the hoop, right, Steph Curry's odds are pretty freaking high, right? So that's kind of the main response to this first objection is, okay, people don't have the information. They aren't this careful. But economics isn't about the process, the thought process that people go through to make economics decisions. We're trying to describe the result. And the result is people do tend to act rationally. Even if they might not have all the details, Steph Curry tends to make the shot most of the time. He's got pretty good aim, right? So that's the same idea in economics. And then the second objection is that people shouldn't act this way, that people shouldn't go around being cold and calculating, weighing the benefits and the costs of every interaction they have with another human being. They have an objection to this idea of self-interest, the invisible hand we talked about back in the last topic. But people do all kinds of wonderful things, and we can still say they're acting rationally. They're weighing the benefits and the cost of their decisions. So people do many altruistic things like donate to charity, donate their time, volunteer. You might be a good example of this. Do wonderful random acts of generosity and selflessness and kindness to one another. And the reason people do that is because the emotional benefit to them outweighs the actual cost of maybe giving something away, donating their time, sacrificing their time, their effort, their money, whatever it is, to do wonderful altruistic things. So this idea that self-interest and weighing the benefit versus the cost of a decision means that we live in this cold, selfish society just simply isn't true. That people do all kinds of wonderful things, and they're still displaying this rational behavior. They're still acting with the benefits outweighing the costs. It's just some of those benefits aren't always monetary. They can be emotional. They can be about connecting to one another. All right, so hopefully that describes our first question about how economists study the economy, the scientific method, some of our assumptions. So this second key question of this chapter is, how do goods flow through the economy? So we are about to look at our first economic model. Now that we know the process, we know the whole point of models, we know it's going to have some assumptions. So the very first model of your semester is going to be something called the circular flow diagram. So it's a model that shows how resources, we talked about resources in the last topic, land, labor, and capital, and final goods, which is when you combine those things and get new stuff, like a Big Mac or a burrito bowl, how do they flow through an economy? So we definitely have some assumptions. We assume an economy consists of two groups of people, households and firms. A household is just an individual, and a firm represents a business. And then there are two markets. So markets, again, we defined in the last topic, which is anywhere where buyers and sellers meet up and exchange. So we have two markets here, the resource market, that's where people buy and sell resources, and the product market, that's where people buy and sell final goods. So this is an example of your circular flow diagram, and I'm going to add a few layers to this. So if you were to sketch this out on your own, some economics professors like you to, you don't have to draw these cute little pictures necessarily, but maybe just simply we could have rectangles representing our two groups of individuals. So maybe this will be my households. And this rectangle over here, that's a better rectangle. This will be the firms. And maybe circles represent our markets. So I think up here is the product market. And down here is my resource market. So the really important part, and you can draw either the resource market up here and the product market down here. You could flip these rectangles. It doesn't really matter. What's really important is that you get the arrows going the right direction. So you want an arrow going from the household to the resource market and then to the firm. Because what that represents is households are the ones who hold our resources. So if households are just individuals, when they go and bring a resource to the resource market to sell, a really good example of this is labor, right? Me as a household, if I'm going to bring anything to a firm, I'm going to offer using my time, my energy, my skills, my labor. And then the firm accepts that labor and they use that labor, they combine it with all kinds of other resources and use it to produce a new product, which is why I need an arrow going from the firm to the product market, because the firm is the one that produces that final product using the labor from the households. And then those products make their way back to households. That's how we get, let's say, Big Macs or burrito bowls or something like that. So that's our simple version. Now at this point in the circular flow diagram, we don't have any money. I just have the flow of resources and I have the flow of products from one market to another. So at this point, our little small simplified version of an economy is using a barter system. So a barter system is when one individual trades another good or service for another good or service. So you have to physically exchange one thing for another. And this is really tricky in societies, because if you're going to barter with somebody, you have to satisfy something called the double coincidence of wants. So the double coincidence of wants occurs when each person who wants to trade with one another has something the other guy wants, the other guy has something that the first guy wants, they want it the same amount, then they can trade. So if I were to barter without money and I wanted to go to the grocery store, I'd have to spend a lot of time and effort going around and finding something that the grocery store would be willing to accept every time I wanted to buy groceries. It's much easier to move away from a barter system and use money. And then if there's kind of this widely accepted thing that everyone's going to accept as payment, like US dollars, we don't need the double coincidence of wants to trade. It's easier to trade if everybody's willing to accept what we call a medium of exchange or money to trade with one another. So we're going to add some money to our circular flow diagram. All we have to do is draw another set of arrows going the opposite direction of the ones we already drew, and I put little dollar signs on them to make them clear. So we started by drawing some arrows from the households to the resource market. So us as individuals, we go to sell our labor to the firm, and the firm is going to pay us back for that labor, not in goods and services, but with a paycheck. So firm offers us money in exchange for our labor. When the firm brings products to the product market that the households want to buy, households pay the firms back with money. And that allows us to avoid the double coincidence of wants. No more bartering. All right, so some economics professors will say this is it. This is the circular flow diagram. This is your simplified version of an economy. But I want to add one more element, which are governments, to our circular flow diagram. The reason I'm adding governments is because we ended the last topic talking about how most economies are mixed economies, which means the government is involved on some level. So governments interact with firms and buy goods and services, and they also hire workers, so they need resources as well, like labor. The different thing about governments is they don't exchange on the market to acquire these things. They get their money from two different sources. Taxes is the primary one, and they also borrow. So they borrow from other countries, they borrow from Americans, they borrow from different agencies within the government by issuing these things called treasury bonds or treasury securities, which is basically like a loan to the government. So governments, they earn their money a little bit differently, but they get access to these products as well. So we're going to stick government right in the middle and connect it to the households and the firms. We're not going to connect them to the markets because they're not exchanging, right? They're taxing and they're borrowing to get these products. But they get final goods and services, and they also get resources. So if you're trying to follow along and draw this, maybe I'll make the government a triangle. You can see I'm not very good at this whole online drawing pad thing, but hopefully it's somewhat legible. Government. Draw some arrows here and some arrows here. So that's it. That's the circular flow diagram as far as I'm concerned. Not too shabby for your first economic model. Definitely a simplified version of reality, showing how products flow through an economy, but definitely explains exchange and using money and stuff like that. All right, so our last key question of this topic is going to be about how economists use data and graphs. So this is just for my folks who maybe haven't taken a math class in a while. We use a lot of graphs in economics because they help us simplify, they help us visualize complex relationships. So we're going to go over some common graphs that we might see in this class, and I apologize in advance to the math whizzes in the class who might think this is a little bit boring, but I just want to make sure everyone's at the same level. So we can show information visually by using different types of graphs. So we are showing one variable or one piece of information in these two graphs. I can show it through a bar graph or I can show it through a pie chart. So my one variable or one piece of information that we're looking at here is the percentage of the athletic footwear market. So if I were to take all the sales in athletic footwear, so think like tennis shoes, and if I were to split it up percentage-wise between the top companies in this market, in this industry, Nike would have over half of the athletic footwear sales. Second place would go to Adidas. They've got a little over 10%. Third place is Skechers. They've got 3 or 4% of the athletic footwear market. And then this other column is every other smaller company combined. So this isn't just one company that has over 33%. These are companies even smaller individually than Skechers here. Just I added them all up so that this graph didn't go on forever. So one piece of information, a percentage of the athletic footwear market. I just label the bars, and this axis tells me what percentage they are. This is a pie chart. It works the same way, but instead of 100% of the athletic footwear shares is what the total circle represents. So each shaded region represents one retailer. So Nike here has over half of the sales, so they have over half of the circle. Adidas is in orange, then Skechers, and then this yellow category, that's my other. These are all the tiny, tiny other shoe companies in there. So We don't have a ton of bar graphs and pie charts, but hopefully you've seen those before and understand how to read them. If I give you a graph with one variable over time, it's probably going to be something called a time series graph. So really this is kind of two variables. So I have time, here I have years along this bottom axis. So think about moving along this line here as moving from year to year to year. And then my variable that I'm measuring here, this is the unemployment rate in the United States, anywhere between 3% and 11% from 1990 to about 2013. So you can see the unemployment rate fluctuates. It rises and then it falls, and then it rises and then it falls. And the highest point in this graph, when the unemployment rate reached over 10%, is a little after 2008 here. And if you know, we suffered a pretty big recession during this time period. So that was our peak unemployment rate. So kind of cool. Shows how a variable changes over time. All right, so now we're going to look at this concept called slope, looking at two important variables. We typically distinguish between an independent and a dependent variable. So an independent variable is a variable that causes the change, and a dependent variable is the one that we're looking to be influenced as a result, what we're trying to measure. So we are going to try to look at the dependent variable test scores in a class based on a variety of independent variables, starting with the number of classes attended. So here I have something called a scatter plot, which are points literally scattered on a graph. So here I have my independent variable, the number of classes that a student attends, here along this horizontal axis, sometimes called the x-axis. And then I have my dependent variable, their corresponding test score, along this vertical axis, which is the y-axis. So this is an xy plane. These points on the graph, that's my scatter plot. So point A here represents a student who attended 18 classes and as a result got an average score of 71 on their tests, excuse me. This represents another student who attended 25 classes and their test score was 82% on average. And student C, who attended 32 classes across the semester, their average test score was a 92%. So every data point when I have an XY plane gives me two pieces of information. That's really key here. The information along this axis and the information along this axis. So two pieces of information here for each individual student. That's what a scatter plot represents. Now, if I were to connect these points, a lot of times instead of putting the individual data points on a graph, I'll just put the line connecting them. And then we'll look at the direction that line is pointing to connect my variables in some way, connect my two pieces of information we were talking about. So here, if I were to draw and connect these points, I would see a line that kind of points upwards along the graph. And so we call that a positive correlation or a positive or sometimes a direct relationship between the variables. It means as I move along this line, either up and to the right or down and to the left, this direction, my variables, this one and this one, they move together. So as I move from this point to this point, they're both increasing, right? At this data point to this data point, this variable increases by 11, right? From 71 to 82. And as I move from here to here, this variable is also increasing by 7 from 18 to 25. So because they both increase as I move from one point to another, that's a positive relationship. But it also works even if I move this direction, right? The variables move together. So if I move from this data point to this data point, I've got this top variable falling by 10, right? From 92 to 82. And as I go this direction, this variable is falling by 7 from 32 to 25. So because they're both falling as we go this way, we still say this is a positive relationship, right? Because the definition of positive correlation and positive relationship is that the variables move together in the same direction. So if I go this way, they're both increasing. If I go this way, they're both decreasing. All right. So negative correlation is the opposite. The line points downward, sometimes called a negative relationship, or sometimes the word inverse is used to describe this. That means as I move from one point to another along the line, either way, sliding this way or sliding this way, the variables move the opposite direction. So I might see this relationship between student test scores and the number of hours they work. So as I move from this point to this point along the graph, I see the hours worked per week is increasing from 20 hours to 40 hours, right? From here to here. But test scores are falling as I move from this point to this point, from 79 to 70. So one variable is increasing while the other variable is decreasing. That is a negative or an inverse relationship. And it would work the same way if I evaluated it sliding this way, right? As I move from this point, if I start here and I move to this point along my graph, now I've got test scores increasing. But as I move from this point to this point, this bottom variable, it's decreasing, right? So when they move the opposite direction, that's called a negative or an inverse relationship. That relationship probably works here because the more hours you work, the less time you have to study, and so the lower your test score will be, and vice versa. The less hours you work, the more time you have to study, and the higher your test score will be. All right, zero correlation. This is when it's a perfectly flat line, so it doesn't point up like the first graph, it doesn't point down like the second graph. We just get this perfect flat line. There's no relationship between the variables. This is what I would hope to see between test scores and your gender, if I were to plot those data points. Now you might be looking at this and thinking, wait a second, gender isn't really a numeric or what we call a continuous variable that you can have fractions of, and you're right. So a lot of times in economics and in other classes is when I have a variable that's a category, like gender, oops, let's see here, what am I doing? Where's my pen? There we go. Let's see if I can draw that better. There we go. So if I have test scores and gender, I use something called a dummy variable, which means I just use numbers and assign them to categories. It's called a dummy variable because the number itself doesn't actually mean anything, right, in terms of numeric value. I just assign them to represent a category. So maybe I assign the number 0 to represent female and 1 to represent male. And then I just plot all my data points on this graph. So I have my 0 point here, and I've got 1 here, and then at the 0 point, I'm just gonna dot and plot all of the female student test scores, and then over here for my male category, we're gonna do the same, and if I plot them all, we have basically a connection that's, for the most part, a horizontal line. That one I drew is a little bit downward sloping, so let's see if I can draw a straight line here. Whoop. That's close enough, right? That's what we would hope for, is that one's not higher than the other. If I did see one that was higher than the other, if it pointed up or if it pointed down, it wouldn't mean there's an inverse or a positive relationship. It would just mean that maybe there's some gender-based discrimination, or maybe you could use it to make some conclusions about how males versus females learn or relate to me as a professor because I'm a woman, maybe the girls do better, or vice versa, right? There's all kinds of interesting social implications you could use here if you were to measure gender versus test score, but hopefully we would see that it's not a variable that's all that important. All right, so another type of graph we might look at is a convex relationship. So this one actually is a combination of all three types of slope we just looked at. So here we see a positive relationship where the line kind of points up. Here we kind of see 0 where it kind of flattens out, and then it turns negative, right? So this might exist between your test scores and how many hours you spend studying. So what does this mean? In the beginning, there's a positive relationship here, meaning the amount you study and your test score move the same direction. In the beginning, the more you study, the better you do on the test. And then past a certain point, that relationship flips. Here, after 35 hours, the more you study, the worse your test score gets. So if that seems perplexing to you, there is an explanation here. Probably this relationship exists because you get a little burnt out on studying. There actually is such a thing as studying too much, where all the information starts blurring together. Maybe you start sacrificing sleep. You're drinking a lot of caffeine to try and stay focused and awake, and maybe it's making you jittery. So there is a point of studying where you max out. Definitely study some in the beginning because it's worth it, but past a certain point, get some sleep, give yourself some rest, or studying too much might cause you to burn out a little bit. So that shape of the graph where it increases at first and then decreases as we move out along this graph, that's called a convex relationship, when it looks like a little hill. All right. A concave relationship is the opposite, where the graph decreases at first, bottoms out, and then turns positive. So you might see this relationship between test scores and the number of times someone cheats. So in the beginning here, the more you cheat, the lower your test score. Past this point in the graph, the more you cheat, the higher your test score. Now, why might that be? If I have some clever students, as I always do, they might notice, well, in the beginning, if you cheat, you're not very good at it. So cheating in the beginning probably isn't going to pay off. You're more likely to get caught, and if I catch you cheating, I will give you a 0 on your test, as it says in my syllabus. But past a certain point, if you keep cheating, you might figure out a good way to get away with it, and then it starts to pay off. Now, the key question here, I am not advocating for cheating at this point. The real question is, what is this point? How many times do you have to cheat before it starts paying off? Because over here on this side of the graph, cheating is not worth it. And so, in my class, I just want to point out here that if I'm to draw this graph, let's see if I can maybe zoom in here. There we go, give myself some more space. If I draw this graph here, my cheating graph here looks like this. If this number is at or above 3, if it takes you 3 times to cheat before you can figure it out, well, in my class, you only have 3 exams. So that means don't cheat once. If you cheat once, it'll lower your test score, right? Don't cheat twice. It'll lower your test score even more. Don't cheat the 3rd time, you'll get an even worse score. At this point in the graph, cheating is not worth it. So if it takes you more than 3 times to figure out how to cheat in my class, it's not worth it. I don't have very many assignments in my class, so don't go around telling people I'm advocating for cheating. I'm just saying that this relationship probably exists and is a good example of something that's concave. All right. So now we're going to talk about some graphs and some data that can be misleading. So we talked earlier about assumptions, how assumptions are very important in order to simplify our model. And we have to simplify our models for our models to be useless and for us to learn anything about the economy. However, if we make the wrong assumptions, they can have disastrous effects in economics. So a very good example of this is there's some very, very smart people, smart economists, very smart accountants and people who work in finance, who made an assumption in the early 2000s that real estate prices would increase forever. And so a lot of models were built on that assumption. And then all of a sudden, in late 2007 and in 2008, real estate prices crashed and it landed us in a recession because people made this bad assumption. So in economics, we need to constantly evaluate and reevaluate our models, and we don't need to overestimate the power of our models or the predictive possibility. We need to be open to the idea that what might have been true in the past or what appears to be true could be misleading. So be very careful of faulty assumptions because there's different degrees of connection between 2 variables. If I see a graph happen and I see a relationship between my variables, there's 3 degrees in which they can be connected. It can be mere coincidence, which means that there's no meaningful connection between the variables. One is not consistently creating a change in the other. There can be correlation, which means these variables are connected in some way, shape, or form, but not directly. There's something missing. And then causation, that's what we're looking for, is when we're trying to predict something in the economy, when we're trying to build a paper airplane, when we're trying to figure out what's making our diet weird with our doctor, and we're manipulating all these variables that could cause the change, we're looking for a causal connection. We're looking for one variable to consistently cause a change in my dependent variable, my test scores, right? So sometimes we can get so caught up in looking for causation that we miss the possibility that it could be one of these weaker forms of connection between my variables. So for example, if I were to go back here to this gender graph that I drew, and if instead of seeing this zero connection here, right, I saw with my dummy variables that the one that I had representing male, maybe all of the male scores were higher than all the female scores, and I saw a graph like this instead of a flat one, I might want to assume, oh man, gender must be causing your test score to change. But the reality is it could just be coincidence, right? We can't dismiss that possibility. So we need to be very careful. It's a common mistake economists and other statisticians and scientists make all the time. So here's an example of this mistake. Suppose you were an economist or a social scientist or a criminologist, and you're trying to predict the number of murders that occur in a metropolitan area. And so you put all kinds of variables to the test. You look at the relationship of other violent crimes, and one of the variables you look at in connection to murder is the number of churches that are in that metropolitan area. And you see this graph emerge when you plot those data points against one another. You see a positive relationship. The more churches there are in a city, the more murders that happen in that city. And you think, oh my gosh, this is terrible. This must be a causal relationship. We have to get rid of all the churches. The churches are causing murderers to run rampant. And you send your study off to a journal about criminal justice reform, right? You've probably made this top mistake, the idea that correlation is not the same thing as causation. So believe it or not, this is a real relationship that exists consistently across cities of the world. The more churches there are in a region, the more murders there are. But it's not because there is a causal relationship. The churches are not causing the murders. There's something missing. And that thing that's missing is the idea of the population. So in a region where you have more humans that live in a specific region, you're going to get more of everything, right? So in a high population area, you're going to get more roads, more grocery stores, more churches, and also more crime, more murders. So churches aren't really the explanation here, the causal change. The real reason that cities that have more churches also have more murders is because the population. So if an economist or a statistician or anybody is making the mistake of correlation not equaling causation, or they're confusing correlation for causation, they're missing a piece of information. In this example here, it is the population adjustment. All right, so here's another example of a common mistake, which is reverse causation. So here in this scenario, it would be easy to see a causal relationship. But sometimes, if you get so set on your model, you might confuse which variable is the independent versus the dependent variable. So let's suppose, hypothetically, you are trying to create a model that predicts the number of times an individual is sick every year. And so you put all kinds of variables in your model that you think will affect their illnesses, the number of illnesses they have. You put in their age, their exercise level, diet information, history, all kinds of things like that. And you also throw in how many times a year they go to see the doctor. And you see a positive relationship here. You see, oh my gosh, people who go to the doctor more often every year become sick more frequently. And so you declare that doctors must be making patients sicker, and so you advise everyone the conclusion of your study is to stop going to see the doctor, and you send your study off to the New York Times to talk about how bad doctors' offices are, but probably in reality it's not a very good study, because I would guess the likelihood is you might have actually reversed the causation. You were so set on predicting the number of illnesses someone had that you actually confused a dependent variable for an independent variable. In reality, it's probably not going to the doctor that makes you sick more often, but the inverse of that, flip that relationship. Probably the more times per year you get sick, the more illnesses you have, the more often you go see the doctor. So if an economist or anybody is making this sort of mistake, it actually makes more sense if you flip which one causes the other. Probably it's more likely the sicker you are, the more frequently you see the doctor, versus the more you see the doctor, the sicker you are. All right, that's it for topic 1.2, economics as a science. Please let me know if you have any questions.